Hello physics students, Mr. Holderman here with a video on Hooke's law. Now Hooke's law describes the force of compressing or stretching a spring, but really it can describe any elastic material. And what do I mean by an elastic material? It's given by the definition here. If you apply a force to an elastic material, it will return to its original size and shape when you remove that force. So many materials can act elastically, most importantly springs, which we will talk about, or tiger tails, rubber bands as well. And if you haven't seen the video of Richard Feynman talking about rubber bands, I highly recommend that. But also everyday objects like bouncy balls, meter sticks, chairs. So in this picture we have a soccer ball that will, it is deformed now, but we know it will return to its original shape. Meter sticks, if you deflect them like I often do in class, they spring back to their original position. And then chairs. I'm always telling students not to lean back in your chairs, but because they will break them. But really what I mean is they'll deform their elasticity enough so that they won't go back to their original shape, which, chairs are expensive, so don't do that. So to summarize, Hooke's law describes the force of compressing or stretching a spring, and let's look at the equation itself and then some examples of it. So we can write this relationship as an equation, and the equation looks like this. F sub s equals negative kx. Now we've seen some of these variables before. First of all, F is the spring force, and we know that forces are measured in newtons, and we've seen the displacement, x, before. So x is the displacement of the spring from equilibrium in meters, m. And k is the spring constant measured in newtons per meter. We'll talk about this a little bit more in another slide. One other thing about this equation is the negative sign. Now the negative sign tells you that this is a restorative force, so it can be either a push or a pull. Let's look at a little bit more about that last bullet, because that's kind of an interesting feature of springs and elastic materials. So that negative sign, it doesn't always show up when we calculate it, but if we look at this example, I think it can tell you a lot of information. So first we're looking at the spring at rest. This is just your normal spring sitting there, no forces are applied to it, and this spring has a box on the end of it. So this dashed line here tells you that it is at equilibrium. So x equals 0. It's not displaced at all. And then over to the right, we see that the equilibrium position, at the equilibrium position, the spring force is 0 newtons. So the spring is not depressed or it is not compressed or it is not stretched, so there's no force on it. Then up at the top, if we compress the spring, let's say we compress it a distance x to the left, so negative x, we are compressing it, we know that it will apply a spring force. So if we draw the force on that object, we have the spring force that acts to push the object to the right. Now we can do the same thing with the stretch spring. So down at the bottom, this example down here, we are going to stretch the spring that same distance, but in the opposite direction. So we have a positive x, and we see that the force on the object is in the other direction. So this is one interesting feature of springs, that it can either apply a pushing or pulling force, compared to something like gravity, which is always going to be a pulling force, as we call it. You can't push with a rope. That tension is always going to be a pulling force, but depending on which direction, whether you compress the spring or stretch it, the spring force can be either a pushing or a pulling force. So I said we'd get back to this K, the spring constant, because we've seen some constant, but let's take a look at this one specifically. The spring constant measures how stiff the spring is. The larger the spring constant, the stiffer the spring. And so the spring constant is specific to each spring itself. It's kind of like the coefficient of friction, whereas the coefficient of friction is dependent on the two materials involved. In this case, the K constant is not a universal constant, but it is a constant defined by each spring itself. So looking at this graph down here, we can come up with that K constant, that spring constant, if we plot a force versus displacement graph. So we can see that we start at 0, and this is displacement from equilibrium. So if we start applying a force to the spring, then, excuse me, we start displacing the spring by applying a force to it, we see that the spring force applied to us it increases linearly. And that happens up to some point, so we keep extending or compressing the spring, and our force keeps going up to this point up here, P. And we see that the spring the force kind of dips down. And we would say at that point it stops obeying Hooke's law, because Hooke's law is a linear relationship between the displacement and the spring force. So you can think about this in terms of your clicky pens. If you sit there at your desk and click your pens, you know that you're compressing that spring, and then the spring is going back to its equilibrium position. But if you unscrew your pen and take that spring out, you can stretch that spring until what we say it breaks. But what really happens is that it stops obeying Hooke's law. It stops becoming a spring and becomes more like a wire. So if we look at this graph, we can get the slope of the force versus position graph, and that tells you the constant for the spring. So we know that the constant is measured in newtons per meter, which makes sense if we analyze the units of the two variables we have here. Newtons, so the slope here we have rise over run, which is newtons per meter. So let's look at one example. A mass of 1 kilogram is attached to a spring. When it comes to rest, the spring has been stretched 0.45 meters. What is the spring constant K? All right, so without the weight attached, we have this spring, and it is fixed on one end. So we can say maybe it's attached to the ceiling, and then when we put the weight or the mass on there, the mass of 1 kilogram, it pulls the spring down. Hopefully that's intuitive. And we know the weight of this 1 kilogram object is 9.8 newtons. So if we were to draw a force diagram on this, we would have one force, that weight pulling down, and the spring force pulling up, and those forces would be balanced. So when that happens, the spring is displaced by this distance x. So we are given spring force, or we can calculate it since we were given the mass initially, and that force is equal to 9.8 newtons. We know the displacement of the spring that it was given as 0.45 meters. And we want to find the spring constant K. So using our equation, F sub S equals negative Kx. One thing to note in these, you won't always use that negative sign, but the negative sign is there to tell you which direction the spring will be displaced. So if we stretch the spring, that negative sign tells us it's going to pull us back to equilibrium. And if we compress the spring, so a negative x, negative delta x, that negative sign tells us that the spring will be pushing us back to equilibrium. So we like to rearrange our equations so that we can see the relationships. So we're solving for k. So the relationship that we have there, k equals f sub s over x. And we can plug in the numbers that were given, and we get a spring constant of 22 newtons per meter. And we can see that the equation makes sense. We got newtons per meter, so make sure your units make sense. But then we also can relate that back to the graph that we looked at in the last example. So we can relate the elastic potential energy to Hooke's law a little bit. We know that forces cause acceleration, and if we apply a force over a distance, we can calculate the amount of work done. We can do the same thing with springs, except springs are conservative forces. Our spring force is a conservative force, so just like our other conservative forces, we can give it its own equation and throw it into our conservation equation. So relating Hooke's law to the elastic potential energy, there we see that word elastic once again. And we've seen this equation before, that the elastic potential energy is equal to 1/2 kx squared, where k is again our spring constant, and x is our displacement from equilibrium. That equilibrium should be right over here. So one interesting note is that when a spring is at rest, it has no potential energy because the displacement is 0. But if we compress a spring or stretch a spring the same distance, x, positive or negative, it has the same amount of potential energy. So over here on the right, we have potential energy if we compress the spring or potential energy if we stretch the spring. So don't forget about your potential energy when you talk about springs, but you can get that K constant from either the force, the Hooke's law equation, or the elastic potential energy equation, whichever information you have in the given problem. So, brief introduction to Hooke's law. Let me know if you have any questions.